welcome grade 12s. Today we're going to do some revision. So we've done a lot of physics and chemistry this term already. So we're going to look at revising your momentum and your vertical projectile motion and of course the organic. Now I wish we could do everything we've done this whole term, but you know it's been a long term. So we're going to get through as much as we can, and what this means is you're going to do a lot of the work today, okay? So I hope you guys are ready. So let's start with physics. We're going to start with vertical projectile motion. So we're going to look at the question. It is there we go. And what I have for you is a question with a graph. And graph skills, grade 12s, have become incredibly important, okay? They are going to ask you about graphs, whether it be in momentum, whether it be work, energy, and power, whether it be in electricity. You're going to get graphs in your physics paper without a doubt, okay? And your graphing skills are important, from being able to draw a graph, from being able to interpret a graph, all of those sort of things. So it's really important that you get this, which is why I've chosen this question, okay? Now, the question says to us, and I want you to have a look at it before I give you time to do anything, that a ball is released from a certain height. The velocity time graph below represents the motion of the ball as it bounces vertically on a concrete floor. The interaction time of the ball with the floor is negligibly small, so we can just ignore it. And then there's the graph. Okay, so there's the graph. And from this graph, you're going to need to interpret some stuff. So it's going to be all sorts of things, from distance to number of bounces to all of those sort of things, okay? So I'm going to give you 3 minutes. Okay, what I'm going to do is I'm going to leave the graph on for a little bit, then I'm going to show you the question. All right, so I'm going to give you 3 minutes to answer the questions, and then we're going to see how far you get. Okay, so you're ready? Make sure you're looking at the graph. Okay, and your 3 minutes is going to start now. So, grade 12s, how did we do? I hope you did okay. I hope you got through most of that. I know it's rather quick, and I do understand that, it just feels like we rush you a little bit with these, but it is about making sure you get through as much of this as we can. And so let's just go back to the question. Ooh, I'm not sure what I'm doing here, but it's all right. That's nothing new. Anyway, so here we have a bouncing ball. Now, there's a couple of things you need to get from this as soon as you start. They told you that the ball is released from a certain height and then allowed to bounce. So what we see from this is that, number one, it's released from a certain height, so initial velocity is 0. And then they plot the graph so your velocity is positive. That means they have chosen down as your positive direction. You have no choice now in these questions as to choose down as your positive direction. So no matter what we do, no matter what calculations we do, down has to be the positive direction, okay, because of the graph. So that's the first thing. Then we look at this and we go, well, what happens here is the ball's going to increase in velocity as it goes down until this point. Then there's a sudden change. And now it starts again, and it's negative. Now, that negative at 0.4 seconds tells me that it's actually hit the ground, and now it's changing direction because it's now negative. And I said anything going down is positive, so now anything going up is negative, okay? Now, before you get all like, oh, but if it hits the ground, it's got to stop. It stops for a fraction, like a minuscule moment in time, and then it changes direction. We're ignoring that, okay? Then it bounces again. At this point over here, at almost 0.7 seconds, it's going to have reached the top of its motion again, and now it turns over. Over here, at 1 second, it changes direction again, so it bounces. It's at the top of its motion at 1.2, and then at 1.4, it hits the ground and stops, okay? Really, there probably should have been a line going down there, because what I'm showing is that there's no continuing motion, so there it stopped. So now we look at this and we go, okay, that actually means that there were 2 bounces. Be very careful. It hits the ground 3 times, but it only bounces twice. There's only 2 points where it changes direction. Okay, so that's really important. Then on a graph like this is we need to remember that a velocity time graph is incredibly useful for us. Remember that the gradient of a velocity time graph always gives us acceleration. So this is free fall, so it really should give us 9.8 when we calculate it. And the area gives me displacement. And because this is a vertical motion question, then the area is going to give me delta y, not delta x. If I wanted distance, I would just ignore the direction, okay? So that's fine. Now we can go to the question. It says to me, describe the changes, if any, in velocity and acceleration of the ball from t equals 0 to t equals 4 seconds, okay? So let's just, I think I've got space, no, let's go back there. I've got space over here to explain it. What happens here? From 0 to 0.4 seconds. Number one, it's in free fall. So acceleration is not going to change, and it's accelerating due to gravity, so it's going to be 9.8 meters per second squared, down. Velocity is going to go from 0 to 4, down, okay? So velocity changes, okay, from 0 meters per second to 4 meters per second, and it's going down. That doesn't change. Acceleration is a constant 9.8 meters per second squared, down. Okay? That's all they want, to change in velocity, change in acceleration. We're all happy. They didn't want anything else from that. They didn't ask about the bounces. And we're just making sure that we get how the velocity changes. And the big thing that they're looking for here is that you recognize that that's constant. Okay, it's a straight line. Now, question 2. this is a really important question, and there's a reason why I've chosen it, because it says, without equations of motion, calculate the height from which the ball was dropped initially. If you use equations of motion, grade 12s, you will get naught. Because you're going to get the right answer, and you have more than enough information to do that, but they are specifying method. So we are testing whether you understand what we can do with the graph. So they only want the height from which it was dropped initially. So that is this part of the graph, okay? Because at 0.4 seconds, it's now hit the ground. So that part of the graph, that line, represents the distance it's fallen. Now we're looking at area because that means displacement. So I want the area of this part of the graph, and that happens to be a triangle. So now we've got to remember some of our maths, and some of us are like, oh, I can't remember the area of a triangle. Guys, you've got to know it's not going to be on your information sheet. So we want displacement, so we want the height, and that height is going to be equal to the area under the graph, okay? And in this case, that happens to be a triangle, and we remember that to get the area of a triangle, it's a half base times height. So this is going to be a half times, and it was 0.4 was the base, that was the time, and the height was 4, and I would expect you to do this on your calculator. Please don't do it in your head if you can't. Please don't feel bad if you can't do it in your head, but it's a half times 0.4, which is 0.2. 0.2 times 4 is 0.8, so it's dropped from a height of 0.8 meters. Okay, guys, you have to show me those two. You have to tell me height is area under the graph. You have to obviously do your substitution, and then don't forget your units. Okay, and I don't need to put a direction on this because it's the height from which it was dropped. We know what it was dropped from, okay? But we would be so lucky that this is all they ask. Never. So now, they add to this. Now, the next part of this question is this. It says, use the given velocity time graph for the motion of the ball, so what we've got, to sketch the corresponding position time graph for the time interval 0 seconds to 0.7. So, 0.7 seconds was here, okay? So we said it went down. Ooh, that's red, that's black. Let's go here. Goes down, hits the ground, changes direction, goes up and stops. Down is my positive direction, okay? So now we look at this and we go, fine. Delta y, it starts from a positive height. So I know it starts up here somewhere. The nice thing about these diagrams, actually, is what I really like about them, is they actually look like what it says. Is we have a ball that's bouncing, hits the floor, and then bounces up to 0.7. What they're looking for here is the shape, that you've got the curve because it's accelerating, so your velocity is changing, number one. Number two, that it bounces at 0.4 seconds. We know that's where it changed direction. And number three, that your height at 0.7 isn't as high as your original height. Remember, I know it's not going to be as high because the final velocity after the second bounce isn't as much. And it doesn't rebound with the same velocity it hit the ground with. Okay? That means we're losing kinetic energy, and some of the energy that the ball had when it hits the ground goes to the fact that it's going to deform, it's got to change direction, and that takes energy for it to change direction. So we know, because it doesn't jump up with the same velocity it hit the ground with, it can't go to the same height. Okay, so that one's quite nice because it exactly looks like a bouncy ball. I like those graphs. And then the last question to do with this one, which we'll do before I give you a break, is the first collision of the ball with the floor elastic or inelastic? So we're trying to remember stuff. Hopefully you would have done elastic, inelastic collisions in momentum. So you're looking, you're going, I've actually really explained it to you. It's got to do with this. It hits the ground with a velocity of 4 and rebounds with a velocity of 3. Okay? There's a change in velocity. That means it's got to be inelastic. So when we explain this, okay, we say, well, it's inelastic. And my reason is that there's a change in velocity. Okay? So the velocity, the initial velocity on the floor is bigger than the velocity off the floor. Okay, it's probably not the best way to explain it, but I'm hoping you understand what I'm trying to tell you. And because there's a change in velocity, that means there's going to be a change in kinetic energy. And as soon as there's a change in kinetic energy, we have an inelastic collision. Okay, grade 12s. So, first question down, time for a little bit of a break, and when we come back, we'll hit some momentum questions. So I'll see you in a little while. Welcome back, grade 12s. Now we're going to tackle some momentum. And once again, I've chosen this question directly, specifically because we don't always see the more difficult ones, and I need you to see that momentum, conservation momentum, elastic, inelastic collisions is valid regardless of the number of things that are involved in the situation. Okay, so here I've got one where there's 3. Okay, and please, before you moan about the spelling of the names, it's exactly how the question was given, all right? So it's not my fault for a change. Not often I can say that, but it's not my fault. So we have 2 boys, Frank and Mandla, I'll try not to butcher that, have masses of 50 and 80 kilograms respectively. They stand on a stationary trolley of mass 180. The trolley is free to move in a horizontal plane, either left or right. The boys simultaneously, which means at the same time, jump off the trolley in opposite directions from each end of the trolley. Both the boys leave the trolley with an initial speed of 3 meters per second relative to the ground. And they're very nice because they give you a diagram. So there's the diagram, and the nice thing about this diagram is that they actually give you all the information. So before I show you the questions, when I give you a time, the first little while what you need to do is you need to actually draw the diagram, and it's a little hard to see the arrow, but Mandla is going in that direction, Frank is going to the left. So I'm going to give you, because if we look at the first question, I want you to calculate the magnitude and direction of this trolley, that it starts to move immediately after the boys have jumped off, okay? So there's a reason why I need you to put the diagram, okay? So I'm going to give you 3 minutes, and you need to use the first 30 seconds or so to copy down the diagram, and then we can go to the questions, okay? So I'm giving you 3 minutes, and we're going to start now. So, grade 12s, how did we do? I hope you didn't panic because there were 3 objects, okay? Because your momentum laws remain the same, okay? So let's have a look at it. Now, the nice thing about this question with the diagram that was given to you is that all the information I would draw in a diagram is right there, okay? Now, they said speed, it doesn't matter. We do mean velocity. What you need to do right on the outset is choose a direction as positive, and it doesn't matter which direction you choose as positive. It really, really doesn't. So I tend to, and it might be because I'm right-handed or because we read from left to right, I'm going to take to the right as positive. That means that when I put in my values for my equation, Mandla has a positive direction and Frank has a negative velocity. Okay, that's the important thing. Because now the first question was calculate the magnitude and direction of the velocity at which the trolley starts to move immediately after the boys have jumped off. Because this is an explosion as such, opposite of a collision, still momentum, we know that I'm going to have to use conservation of momentum. So that means that the sum of the momentum before, okay, is equal to the sum of the momentum after. Okay? Now before, the 2 boys and the trolley were one object. So beforehand, I have the mass of Frank, the mass of Mandla, and the mass of the trolley, and their initial velocity. Afterwards, Frank has a final velocity, Mandla has a final velocity, and the trolley has a final velocity. Okay. Beforehand, when we go back and look at the diagram, they said to us that, well, they were all 0, so that's great. We like that. Yay, makes life easier. That means initial momentum is 0. Now, Frank had a mass of, wrong way. Wrong way too again. Frank has a mass of 50, Mandla has a mass of 80, so we're going to remember that, and we go here. So Frank has a mass of 50. Now, we said I chose to the right as positive. Frank was moving to the left, so that becomes minus 3. Okay. Mandla has a mass of 80. It was going to the right, so that's 3. And let's just check what the trolley's mass was. Look, 180. So that means we go here. And you know what? The science is done. Now it's a math problem. Okay, because now we have to solve for ft. So that's 0. 3 times 150 is, 50 is 150. Okay, 3 times 80 is 240. And I'm just showing off right now, so just ignore me, because I can. I like numbers. Anyway, moving on. So, we have to solve for ft just because of time. I'm going to, well, let me show you. 150 minus 150 plus 240 is 90. Okay, that 90 is going to have to go over to this in that direction. Okay, not in that direction, to the left-hand side. So it's going to be minus 90. This, that's not, I don't know what that was that we just drew. That was supposed to be a 1, not a 7, 180 F. Trolley. So now I get, because now I'm going to go 90 divided by 180, which is 0,5, but it's minus 0,5. What does that mean, grade 12s? Well, I chose to the right as positive. So if I get a negative answer, that means that the trolley is going to go to the left. Don't forget to put it to the left. Or you could say towards Frank, away from Mandla, any one of those. I can say to the left or the right simply because I was given a diagram. Okay, without a diagram I couldn't, but with a diagram I absolutely can say to the left or the right. Then, give a reason why the velocity of the trolley calculated in 2.1 does not remain constant after the boys have jumped off. This is just very simple. There's going to be friction. The trolley will eventually stop. because there's friction, and the friction is a net force. It's an external force which will stop the trolley from moving. That is a good thing. Okay? Good. Now, this is the one where I thought you might struggle. Explain using Newton's second law why the trolley moves in the direction as calculated in 2.1. So they're asking you, why does the trolley go to the left? So let's go back to our diagram. And we've decided that the trolley is going to go to the left. Okay? Now, we've got to say to ourselves, okay, this gets a little bit more complicated to describe. Remember, and this has to do with Newton's third law, when Mundler jumps off the trolley, he's going to push backwards onto the trolley. At the same time, the trolley will push forwards on him. It's Newton's third law, okay? Frank will push backwards on the trolley, and at the same time, the trolley will push forwards on Frank. Now we've got to consider the fact that it's going to the left. That must mean that the force that Mundler is exerting is bigger than the force that Frank is exerting. And that has to do with this change in momentum, okay? Mundler is going to experience a greater change in momentum. He's got a bigger mass. If he has a greater change in momentum, and remember this is, oh look, it's gone black, that's great, F net, or purple. Look, we're doing multicolored today, it's great. F net, I want delta T there. Okay, no, I want that. Sure, it's really not liking me today. Who knows? Thought we'd do it nice, is equal to change in momentum. And delta T is going to be the same for both. Mundler is going to experience a bigger change in momentum because he has a bigger mass. That means the net F net he experiences is going to be bigger. Okay, therefore, he's going to exert a bigger force on the trolley. And if Mundler exerts a bigger force on the trolley, remember, the net force will then be to the left. And your object will accelerate in the direction of the net force. Okay? So that one's a bit of a mean one to try and explain. So let's try and put it in words because I think it's quite important that you're able to write this down. Okay? So when we write this down, extension. He doesn't like me again today, but we all know that this machine hates me. And I'm so nice to it most days. Okay, so this is what we write. Mundler has a greater change in momentum. Okay. Therefore, he experiences a bigger F net. Okay, so we're all happy with that. And now, due to Newton's third law, Mundler exerts, it's a good way to put it, a bigger force on the trolley. Sure. See, it's changing color again. It wants it to be all pretty for you. I have no idea why it keeps doing that, but that's okay. Apparently it is my... Okay, so bigger force on the trolley, and therefore, according to... We don't like questions like this, eh? Because it takes too much writing. To Newton's second law, the trolley will accelerate, or accelerate's good. Will accelerate in the direction of the net force. And we really don't like questions like that because that's about 4 or 5 marks. Lots of explanation, but it's a really nice one, guys, because I'm testing lots of Newton's laws in there, okay? We're not quite finished with this question, but I think you probably need a bit of a break. I can hear the brains are tired, especially for early in the morning when you're watching this. So I'm going to give you a short break, and then we'll come back and we'll do a little bit more on this before we hit chemistry. Okay, welcome back. Last section, we can push through. Let's do the last question of this one because it's really important, okay? So what we have here is we have the whole situation again, okay? Now make sure you still have all the information you've worked on the last few questions because you needed to answer this one, okay? So now, it says the time it takes for Mandela to push against the trolley with his legs is 0.2 seconds. During this time, the trolley exerts a force on Mandela, which we've already done. Calculate the magnitude of the force the trolley exerts on Mandela during the time it takes for Mandela to push against the trolley. Very important question. So I want you to try it. I'm giving you a minute though, so you're going to have to work quickly, okay? You've got a minute to try this, and then I'll go through it with you. So you've got a minute, and it's starting now. Okay, so we're done, grade 12s. Or some of you go, no, I don't even know where to start. It's all right. Don't panic. Worst thing you can do in an exam is panic. As soon as we've got a momentum question, which then goes towards force and includes time, it's an impulse question. So that means the way we do this one is we go, well, F net, because we want force, delta T is equal to change in momentum. That's all it is. We want F net. We are told that the collision takes, or the explosion takes 0.2 seconds. Oh, that's not a 2. That is, though. And change in momentum means we take the mass. We're looking at Mandela, so it's 80. And we take his final velocity minus his initial velocity. And now we solve for F net. So this means we're going to have F net times 0.2. And this is 3 times 180, which is 240, which we're then going to divide by 0.2 on both sides, and we get F net is 1200 newtons. But it's a force, and they said time it takes, calculate the magnitude. Okay, that means we don't need direction, but if we did need direction, it would be towards Mandela or to the right. The right would probably be better. Okay, next question says, explain why Mandela accelerates towards the right if the force exerted by Mandela on Mandela by the trolley and the force Mandela exerts on the trolley has the same magnitude but acts in opposite direction to each other. So what they're asking you here is, why does he move at all if you've got 2 equal forces acting in opposite directions? This is a Newton's third law pair question, okay? The forces act on different objects, okay? So it's because the forces act on different objects, okay? So because they're on different objects, they don't cancel out, okay? Therefore, they don't, there we go, cancel. That is so important here. They'll ask that often. okay? But with Newton's third law, equal forces, same magnitude, opposite direction, but they're on different objects. They can't cancel out, okay? Now, I'm going to hear some groans and I'm going to hear some cheers if I could, because now we're going to go into some chemistry. And there's always those of you who love the physics and go yay, which is me, and then those of you who like chemistry, which isn't really me, so you get all sad. But it's okay, we have to do it. We're going to do some organic. So let's get to those of you who like organic. Here we have a very nice question. I have some chemical organic compounds. There's my 6 compounds. I have a whole bunch of questions for you. So I'm going to give you 3 minutes, and then we're going to see how far we can get, okay? So you're going to have 3 minutes. There's the compounds. Look at them. You're going to need them as reference, and I'll go between the 2 questions to help you, okay? The 2 slides. So I'm giving you 3 minutes, and it's starting now. Okay, great, awesome. Now, I'm really hoping that for the next few minutes, some of you are going to be bored out of your minds because you know how to name your organic compounds so well that this question was just a walk in the park. So that's what I really want, okay? If it wasn't, it's okay. You've got plenty of time to learn it, but it's really important that you get this section, okay? And what I'm going to do now with you is I'm going to show you how you work through a question like this before you even look at the questions. Now, because you don't have it in front of you on a piece of paper, it's a little more difficult, but now watch what we're going to do. So you look at this question. As soon as they give me a table like this, I know that they're going to ask me questions like, what is the name, draw it, what is its functional group, is it saturated, unsaturated, maybe it's going to have something to do with isomers, maybe it's going to have to do with bonding, there's an ester in here, maybe it's going to be esterification, who knows. So the first thing I need to do is I look at each compound and I go, fine, identify the functional group. So in A, there's a double bond that makes this an alkene, okay. And just because we can, we're going to name it. And we're going to 1, 2, 3, 4. It's 4. So that makes it butene. The double bond's on number 1. So this will be but1ene. Okay, good. We're happy. Then the next one, we look at it. It's got a halogen on it. That makes it a haloalkane. Okay. It's actually got a methyl group as well attached over there. So if we had to name this one, we've got 1, 2, 3. That makes it propane. And on number 1 is the bromine. So that makes this 1 bromo. And you have to give me the methyl group for this one. 2 methyl propane. Okay. We're all happy. Then we look at the next one. And we got all single bonds. That makes this one an alkane. We're happy with that, and there's a methyl group there, methyl group there. That makes it a dimethyl. Okay, and we're fine. And there's 1, 2, 3, 4, 5, 6. 6. It's meth, eth, prop, but, pent, hex. So it's hexane. Okay, and the methyl groups on 1, 2, 3, 4, 5. So 3 and 5, or 1, 2, 3, 4. 2 and 4 is better. Okay, so we've got that one. Then we've got methanol. It's an Al. That makes it an aldehyde. Okay, an aldehyde is terminal, remember? Okay, it means that the double bond oxygen goes at the end. It's methanol. Well, it can only be terminal. It's methanol. Meth means 1, so it will look like that. That's methanol. Then we go here and we say, oh, look here, we've got a carboxyl group that makes it a carboxylic acid. Let's break this down a little bit. So we have a carboxylic acid. And if we had to name this one, this is actually ethanoic acid because there's 2. And I'm hoping you guys all know that this is also known as acetic acid, which is otherwise known as vinegar. Then we have methyl methanoate. It's a double barrel one, which makes this an ester. Okay. The methyl comes from methanol. Okay, that's the first part, so we know which alcohol it is. The methanoate means it comes from methanoic acid. And I'm writing all of this down because often they'll ask you for an ester. How's it made? Write the formulas. What does it come from? And this is what we need. So probably going to need to draw it as well. So methanol, methyl means it's got single carbon, then the oxygen, then the methanoic acid, double bond, okay, and then it would be my necessary hydrogens. Now, grade 12s, I've probably done more than I needed to on this, okay, but one, I'm hopefully teaching you some extra stuff on what, if you didn't know what the different things were. But 2, I now need you to see how quick it is for us to do the rest of the questions, rather than us having to go back and forth and going through each compound again to see if it fits into the question, because we've done it. Okay, so now we go to the question, and the first question is, write down the letter that represents an alkene. So we go, hang on, wait, where was the alkene? It was A. Don't even have to think about it. So we go back and we say, well, that was A. Where was the aldehyde? So we go back to our question and we go, the aldehyde was D. Don't have to think about it. There we go. Oh, look at the next question. Write down the IUPAC name of B and C. So we go back to our table and we go, well, let's see what I did. Oh, look, I named B. I did it. I don't have to think about it again. Though if you didn't, you can. But now I'm going to write it nice and neat, okay? So B, when you write it, is 1 bromo, 2 methyl, and it's propane. And remember, the methyl and the propane, did I spell methyl right? Yes, I did, are one word. Okay, one word, very important, okay? So that's named. Now they say write down the name of C, which we also named 2,4-dimethylhexane. I don't even have to think about it. Okay, so now we can write it down, and it's 2 comma 4. Don't forget the di, because they're 2 methyl groups, so it's dimethyl. And we said it was 6-hexane. Grade 12s, they are incredibly fussy with naming, with the dashes, with the numbers, with the spelling, with the spaces, incredibly fussy, okay? You have to get it right. I'm sorry, I know it sounds petty, but that's the way it is, and you want to make sure you don't lose marks on silly things. Now they say write down the structural formula of compound D. Let's go back to D. Oh, look, it was the methanol. We've done it. Don't even have to think about it. We've got it. So now we just do it neatly, okay? So now we've got the time, so we go methanol. There we go. There's my methanol. And then they asked me to write down the name of the carboxylic acid shown in the table. So now this is a two-way thing, because now I've got to recognize the carboxylic acid, which we said was E. We named it straight away. It was ethanoic. So now I can go back here and I can go ethanoic acid. Okay, 2 words, very important. Oh, and look at this. Write down the structural formula of F. Did we not do that in the middle? Of course we did, because we're amazing. Okay, well, of course we are. We're doing science. So methyl methanoate is what we had. And so we are now going to go methyl, meth, and O8. So that needs another hydrogen, that needs another hydrogen, that needs a hydrogen. And there we go. We're done. Nice and easy. With any organic question, guys, work through any diagram, even with the functional groups. Unfortunately, we're not going to get to a reaction question today. But when they give you a flow diagram, work through it. Name things, draw things, work out which reaction it is. Work out if it's substitution, addition, whatever, then look at the questions. You are going to save yourself a lot of time, okay? Plus, you don't then need to, you're not going to get yourself into a bit of a tiz, because you're going to start rethinking about things, and then you're going to, oh, what if I'd got this? And if you write it all on your question paper, it's there. You don't have to think about it again, because sometimes you think about it and then you forget. Write it down, okay? Write it down. It'll be much easier that way. Okay, so grade 12s, I have to go. We did a lot of work today. Well done, and I will see you again next time.